Good morning. I'd like to thank you for coming here today. So very happy to introduce a presidential lecture by Professor Peter Zoller, who's a professor of theoretical physics from Innsbruck University in Austria, where he works on a number of topics, but largely relates to atomic physics and theoretical quantum optics, also many-body quantum physics with quantum gases for quantum information. And he works very close in experiment. And at this point, I'll just say there's always been a long tradition in Innsbruck of experimentalists and theoreticians collaborating very well together, which has led to several marriages, for example, that of Giovanna Marigi and Jürgen Eschner. But aside from his physics, he's got many claims of fame, the most important probably being telling us how to build a quantum computer. And I've just come back from a conference on quantum technologies where the advances that are being made are actually quite amazing. Feel a little bit that we're falling behind here and we need to really work and keep in touch with this topic. So we're very lucky to have Peter here to tell us more about it. He's also scientific director at the Institute for Quantum Optics and Quantum Information of the Austrian Academy of Sciences, while based in Innsbruck, has over 400 publications, and interestingly, an average citation per paper greater than 80. Okay, try beating that. He's won many awards, and just the most recent ones are in 2008, the Norman F. Ramsey Prize from the American Physical Society for work on quantum computation, communication, and simulation with trapped ions, atoms, and molecules. 2018 also, the Willis E. Lamb Award for pioneering work in quantum optics and quantum information. 2016, the Herbert Walter Award from the German Physical Society and the Optical Society for pioneering discoveries and development of new interdisciplinary quantum science unifying quantum optics, atomic, molecular, optical, and condensed matter. And in 2013, the Wolf Prize in Physics for groundbreaking theoretical contributions to quantum information processing, quantum optics, and the physics of quantum gases. So while Peter is currently here for 3 days, he will be hopefully returning in September if anyone would like to meet with him and doesn't have a chance during his fairly busy 3 days here at the moment. So thank you very much.
Thank you very much for introducing me here, and I have to say that I've enjoyed very much the last 2 days that I'm actually spending here, both in terms of science, but also I like the scenery here. You know, you have a very beautiful place here. So I was asked today to give this presidential lecture as a public talk, in the sense of telling you a little bit about quantum physics, about quantum computing and what we're doing, and I will do this very much, of course, from my personal angle, the kind of systems, the kind of collaborations that we've been involved, and of course, right now, quantum physics is a very hot topic, and there's a lot of people out there, also lay people, that are interested in this thing, and I will try to convey today a little bit part of the excitement, but also the information which is behind this thing. You might wonder what this picture is. This is a painting at our Academy Institute at the entrance, and it shows Erwin Schrödinger as one of the founding fathers of quantum physics. Is very, very close to where we have our institute, just a few kilometers away. And on the left-hand side down here, you can see his famous Schrödinger cat. And we will talk about Schrödinger cats today. We will breed them, but don't think about real cats. We will talk about, you know, cats in another sense, cats that do actually or correspond to quantum computing. So let me start with my talk. As you could see, I now gave the title to my talk here, Quantum Computing and Quantum Simulation, from quantum science to quantum technology. Of course, all of us are physicists, quantum physicists. We are doing basic science, but the interesting part at the moment is the connection that we are building towards a new quantum technology. And I think that this quantum technology will be one of the probably most important developments that we will have in this century. There's this picture here in the background that you can see here, and I'm seeing some of you looking at that and already wondering what this picture actually corresponds to. Let me explain a little bit about it. I mean, this is an Innsbruck experiment which is down in the basement in the group of Rainer Blatt. He's my experimental colleague. Here's an ion trapper, and what I mean by ion trapper is that he's able to prepare single atoms. These are images of single atom. That's one ion over here, that's another one over here, that's another one over here. And ions, of course, are particles that have a positive charge. Atoms with a positive charge, they repel each other. You can trap them in the vacuum chamber. You know, that's a vacuum chamber that you can see back here. And in there, you can just hold this string of atoms or string of ions in free space. And of course, what we want to do is this, that we want to use them as memory cells to store information. And at that point, some of you might be very impressed by the fact by saying, wow, that's really the ultimate. You know, we are taking a single atom and we are storing, say, 1 bit of information. And in each of these atoms, it cannot go smaller. Actually, what you should be impressed about is not so much that this is sort of, you know, single atoms storing some information in the sense of classical computer science. But I will explain in my talk today that what we have is that we will actually use quantum mechanics here, or have quantum mechanics at work. And actually, this will correspond to the Schrödinger cats that we have here on the left-hand side. You know, Schrödinger's famous cat that corresponds to a cat being alive and dead at the same time. That completely, you know, is counterintuitive from our classical intuition. But quantum mechanics, I mean, really has these kind of things, and we see it in the lab, and we are now at the point where we make Schrödinger cats sort of do our computation, and this is really what this quantum computing and quantum physics is really all about. I'll tell you more about this system then a little bit later, but let me sort of give you the bigger picture of what we are trying to do now is this, that we will talk about information technologies of the 21st century, in particular this quantum computing and quantum information as we call it, and don't see this as a linear extension that we are just trying to have computers, you know, the computers that we know, that we have here, to make them smaller and maybe therefore more powerful. You should really understand these things as being a new paradigm. You know, we are doing something qualitatively new, something which is sort of, in principle, fundamentally much more powerful, and this is the power that we are trying to unleash here at the moment. If you start out talking a bit about the sort of progress in technologies, just in the context of, say, classical computing, that all of us know so well, it's interesting to look at the history. You know, if you go back in time, we had computers, you know, based on radio tubes that were huge, you know, filling whole rooms. Of course, then semiconductor industry came along, you know, integrated circuits, chips, and all of these things. You can see that by these things developing over time, systems became smaller and smaller as it was faster, smaller, and smaller. What I will be talking about here today is this, that we sort of go to the ultimate where we talk about single atoms, or maybe single electrons that will store this information. But then the important point being, of course, that you're going from here to over here. If I talk about single atoms, the world of quantum physics become very important. We have completely new rules, and we are trying to exploit them in this novel way, which is really what quantum information is actually about. I guess most of you know this gentleman over here. He's one of the most successful entrepreneurs. You know, he founded Intel, and there's the famous Moore's law. And there's various ways to present this Moore's law, but let me just give you one example for that. And this is, I've plotted over here the number of atoms per bit that is necessary in one of the cells and the computers that we have over here in order to store our information. And you can see how this thing over the time sort of progressed. You know, there's these landmark, you know, processors that we had over here. And if you take this line, I copied this a few years ago, it really crosses 2017. And in 2017, I looked up, does it really now cross the point where we have one electron, for example, storing really 1 bit of information? And indeed, there were papers from IBM, for example, that demonstrated these things, even, of course, they have not made it yet into our product. So what you might wonder at this point is that, well, you know, we are getting smaller and smaller and smaller, faster and faster and faster. And of course, in going down here, we have single electrons. Well, do we have half an electron to make these things even, you know, smaller or so? At that point, you might say, well, there's no half electron, and so how can we then sort of get smaller in this sense? And you might conclude that quantum mechanics at that point sort of starts to take it away from us. It makes our life much more miserable. But you will see now the following, that quantum mechanics, by going down, you know, all the way from these original computers that were constructed, I don't know, 50 years ago, half a century ago, all the way down to the level of one atom, that something really qualitatively new happens. And it is this qualitatively new that will, of course, you know, be the topic of the talk that I'm giving here today. Let me put these things in a somewhat broader perspective and quote, first of all, Rolf Landauer was one of the heroes at IBM, as one of the theoretical physicists there that thought about information and physics and all of that. And there's this very famous quote from him that says, you know, information is physical. And what do we mean by that? Well, what we mean by it is this, that when you, for example, have a computer like the one that I have here to use my presentation, then it always, corresponds to some input that we have in our memory cells, our zeros and one. There's some processor inside that does something and then producing an output. But from a conceptual point of view, what you can see over here, this doesn't really differ at all from the abacus that, was used in China many, many thousand years ago in order to do some computations. The only actual difference, to the computers that we have today is this, that this is, of course, much, much faster that I have here, rather than this thing, which was very slow. So the usability of this thing, of course, has increased. This is much more powerful. But the basic underlying concept, of course, is just the same, which it always was then actually 1,000 years ago. So our information processing that we talk about here today is actually based on our classical understanding, or sort of on classical computing, because this is really a classical mechanical device. And the only thing that changed is this, that it just got much faster. Some of you might argue at this point, well, there's of course some semiconductors inside or so. But at the end, the way how we use it is just really, it's just much faster than what this thing is over here. So in that sense, you might say information is physical, because at the end, when we perform computations here, it just corresponds to some beats that we are moving around according to certain protocols and to certain algorithms that we have. So in that sense, you might say computing, first of all, is a physical process that has to do with physics, okay? And the classical computers are the ones that correspond to this classical mechanics, if you want to. And our present computers process information according to the laws of classical physics. But then, of course, it was in the beginning of the 90s or so, even a little bit earlier, that some people, made statements, and I particularly want to quote here, for example, David Deutsch in Oxford, who is a mathematician and physicist, know that at the fundamental level, of course, nature, as we know, is not the one of classical physics, but actually obeys quantum theory. So at the fundamental level, information science should then also be a quantum information science. And we might ask ourselves, what's the difference between this classical information science and the quantum information science, that we would like then to talk about now here today. There's various, perspectives in this context from the technology, can we beat Moore's law? Computer science are the new complexity classes from the physics, and of course I'm a physicist, I'm interested in that, is to learn more about quantum theory, because essentially what we're going to do by sort of breeding Schrödinger cats in our labs, we are trying to do something where we are sort of pushing the boundaries and investigating quantum mechanics to the more and more macroscopic. And by pushing the boundary, we get something very useful out, quantum computers. But at the same time, it's also a very fundamental test of quantum physics, because we push it into a domain that so far there have been no experiments. And so if a quantum computer works, it will be a fantastic outcome, but it also proves that quantum mechanics is right. Maybe at one point we might even discover that quantum physics, in the way we understand it today, is incorrect, maybe due to some quantum gravity or whatever the underlying reason is. And then, of course, this becomes a very important challenge to quantum physics. There may be some new physics that we discover on the way. So it's kind of a win-win situation what we are discussing here. Either we get quantum computers out as something very powerful, or we will discover some new physics. I think on the short run right now, we will just get machines out that are very interesting, really proving that quantum physics is wrong. I think I will not probably live to see that, but who knows? I mean, this is what we are asking here. Well, quantum mechanics, the way that we know it right now, is actually about 100 years old. I guess that most of you know that it was Max Planck, really in 1900, that sort of discovered the Planck Constant, h bar, h or h bar, that was introduced as a little helper constant. The symbol h comes from German, it's like the helper constant. He had to introduce a constant. He didn't really know what it was, but he needed it in order to fit his data of black body radiation. And it turned out that this h then was sort of propagating, Niels Bohr understanding atomic physics. The way that we understand quantum physics today was really written down by this gentleman, Schrödinger, Heisenberg, and so on. And here's, of course, this famous Schrödinger equation, the most elementary form. This was the time evolution over here, and this is the corresponding timeline where all of these things happened. This is sometimes what we call the first quantum revolution, because at that point, things were written down that that let us understood for the first time quantum chemistry, nuclear physics, and then sort of, all of these developments that eventually led also to elementary particle physics. This was the foundation of the quantum physics that we know actually today. But it's kind of interesting that, clever minds like, for example, Einstein over here, or then Schrödinger, with his Schrödinger cat, very early on pointed out that actually this quantum theory had certain paradoxes. In these early days, this was in the 1930s and 40s maybe, one was not able to test some very strange predictions of quantum mechanics in the lab. And Schrödinger's cat simply said, well, we have here what we call superposition states, and I'll talk about this thing now in one moment, what we mean by that. Like a cat being alive and dead at the same time, that obviously completely, is not what agrees with the intuition that all of us have. And I think none of us ever met on the street, the dead and the live cat at the same time. That, as I said, we will afterwards construct these Schrödinger cats in our quantum computers, and they will be, of course, cats of a different type. But what happened sort of, around 70s, it was people like Feynman who said that started to take some of these paradoxes seriously. And right now we're in the phase where many of these paradoxes and strange phenomena that we see as counterintuitive make it into the lab, and we see them every day in our experiments. But if they are strange, if they are paradoxes, why not use them to do something qualitatively new? And this is what we sometimes call the second quantum revolution, where we think about quantum computers, Shor's algorithm, quantum simulation. And I'll talk a little bit about these things here today, both in terms of building devices, and the enormous progress that was made is sort of that, we have an evolution right now where from these paradoxes of quantum mechanics, we're going to these practical applications where really then practical devices come out that surprise us in terms of their abilities and what they're able to do, and quantum computers just being one of these examples. This is what we call the second revolution, and of course that's sort of going on, I would say, right now. I know that here in the audience there's some people that are not experts for quantum physics, so let me give you a 5-minute crash course in quantum physics, okay? What you always knew, but I just remind you of some of these things and sort of put my finger on a few, of these strange places that we have in quantum mechanics. So let me take you back to school for just a few slides and then progress and really talk about what's inside of our quantum machines, okay? All of us, I guess, know this famous, double slit experiment that I'm going to tell you now and illustrate by a little movie. Like we have here, for example, in classical physics, some screen that we have, a little cannon. This is shooting out here classical particles. And of course, if I just got one slit and I'm shooting particles that are at random through the slit, what you will get is sort of the obvious. There will be, one line over here back. And imagine that you now open also a second slit over here, and again start shooting particles with your cannon out here. Again, these are classical particles. You find, of course, the second line over here. So the obvious thing happened. And let me right away make an analogy. When I have a little a memory cell in my computer, a classical computer sort of, stores a 0 or a 1. It's 0 or 1. Like, here the particle goes through one slit or goes through the other one. In quantum physics, these are quantum particles that we have here, electrons, photons, and so on, and I take a double slit over here. The strange thing is that this is particles and waves, and how does this thing manifest itself? Well, it sort of manifests itself that if I shoot a quantum particle over here, I do not get the two stripes that we had over here, but we get an interference pattern. And how do we understand an interference pattern? Well, on one hand, these are particles that we are shooting. On the other hand, there seem to be properties like we know from, for example, water waves here. When we have water waves that propagate across a double slit, there will be interference of this and then giving rise to these interference fringes. So this is this very strange thing that, a particle does not go through one or the other slit. It can go actually through one and the other slit at the same time if you want to. This is sort of what makes quantum mechanics very strange. And we call these things superposition state, but what it means in terms of computers is this. As I said before, classical memory cells of a computer can store the 0 or the 1. And quantum mechanically, it simply means you can sort of store 0 and 1 at the same time. So you can also see a kind of a first glimpse why some of these ideas might actually be more powerful and also sort of interesting. So we call this thing a quantum mechanical superposition state. And let me just tell you at this point a little story of my colleague, Ignacio Sirac in Munich. Is one of the Max Planck directors there, and we did many of these ideas about quantum computing here directly. He said that he originally started out becoming an engineer and for aerospace science, building airplanes and so on. But then he was so intrigued by theoretical physics that he switched to become a theoretical physicist, and obviously quite a good one, I would even say. Yeah. When he switched, his grandmother got very concerned. I said, "What are you studying there?" She said, "Oh, I'm studying now quantum physics." And she said, what is actually quantum physics? He said, "No, in quantum physics, we study phenomena where a particle can be here and there at the same time." And his grandmother looked at him and said, "It sounds very interesting, but please don't tell anybody, okay?" So I'm telling you about this thing here today because it's actually true. Particles can be here and here at the same time, like being zeros and one at the same time in quantum computers. Otherwise, I guess I would not give my talk here today. Okay, so let me take you back now to this machine that I want to talk about, and let me tell you, or sort of teach you a little bit about the ingredients that are behind this thing and what quantum mechanics means now in terms of storing bits and what we call then quantum bits at the end. So when we have a classical bit, it is either 0 and 1, and the way of visualizing this is sort of, it's like it takes on two values, either 0 and 1. This is what we store in our classical computer memory cells. Quantum mechanics, I said before, allows to be 0 or 1, but sort of also everything in between, sort of storing zeros and 1 at the same time. And one way of visualizing this is what we call the Bloch sphere, where the north and the south pole that correspond to the classical values are over here. But quantum mechanically, all of the other things on this sphere are also allowed, like states where we have a 0 and the 1 existing at the same time in your computer. And this is what we call these quantum mechanical superpositions. And one pictorial way of illustrating this, I stole this picture from somewhere at one point. I don't even remember exactly. If you look at this picture here, you can either see an old woman over here, here with a mouth and so, or you can see a very young woman here with a nose. And so, it's one or the other, depending how you look at it. Of course, I'm not saying that this is quantum physics here. This should simply illustrate to you that, depending how you look at it, it can be both. And of course, quantum mechanics is a little bit more sophisticated in the picture that we have over here. So, of course, if I got now one bit, or then one quantum bit, we just have now, one sort of memory cell that can be in this superposition state. We can, of course, then also do quantum registers in the sense that I can take then, a first register where a first one, where the first one stores 0, 1, the second 0, and the third one. Quantum mechanically, of course, if you got 3 of these quantum bits, I have at the same time, the possibilities of all of these numbers stored in my quantum computer. And when I talked before about Schrödinger cats, being dead and alive at the same time, you can really see what I mean by that over here. At the same time, you can store 0, 0, 0, 0, 0, 1, and so on, all of these combinations. And this is what Erwin Schrödinger identified as one of the most interesting aspects, of course, of quantum physics, which is entanglement. And just to give you the feeling how large, and how powerful all of these things is, if I take n qubits over here and say take n about 300, you have here 2 to the 300 possibilities that are stored at the same time, in your quantum memory. And how much is actually 2 to the power 300? Well, if I take all of the, visible universe that we have out there, and I take each of these particles that we have there as a memory cell, this is how much classical memory you would need in order to represent, a quantum state that really consists of the superpositions of all of these possibilities. So you can see right away, well, this is space. We make the joke, of course, that this is a huge Hilbert space that we have here. And this is really what Feynman pointed out on very early on, is that, we should actually exploit these possibilities that we have here in order to produce quantum machines that use these superposition principles, this entanglement, in order to then compute, either in the context of quantum physics or maybe some algorithms and so on. So let me now take you a little bit inside, this quantum computer, what they're sort of built off and what the various elements are, because at the end we are interested in constructing one, and I showed you the ion trap at the beginning, and this is what I would like to take you to. So this is again this picture. We have an input over here. Think of this now being as our quantum bits and our quantum register. This is a quantum processor that acts, see this as a timeline sort of going up here. And if you start to look inside, I mean, what are these wires sort of that are making up our quantum computing? Well, they correspond, like in classical computers, to certain gates. We perform certain operations on these quantum bits, you know, that involve maybe one of the quantum bits, maybe a pair of these quantum bits, like the gates that we have over here. And there's very strange kind of gates. I mean, gates that do not exist classically. One example being what we call the Hadamard gate, where you put in a 0, but what you get out is a superposition of 0 and 1. Or you put in a 1 and you get a superposition of 0 and -1 over here. So see these gates, the single qubit gates, just essentially as you know, a rotation on this Bloch sphere that we can rotate between any points over there. And these are, of course, operations which do not have a classical counterpart. It gets even more complicated and interesting and also tough at the end to implement. We talk about 2 qubit gates. So depending on the state of our first system, you know, for example, if this thing is pointing down, it should act as nothing on the second one. It just leave this thing unaffected. And if it's up, then it should simply perform a certain kind of rotation. So we have these kind of gates, and it turns out that if you are able to implement these operations, single and 2 qubit operations, you can actually decompose the most general thing that you want to do and can do, always in terms of that. So at the end, the question is how do we build these kind of gates in this context here. And let me emphasize that these are quantum gates. They sort of look very classical in the way that we draw it. They act actually on all of these quantum superpositions that we have in there. And this is something that we call quantum parallelism, that we have here a quantum register in a quantum mechanical superposition state. And our quantum gates, they really act, you know, on these superposition states on each of the component of this whole wave function that we have in there. And this is sort of, you know, what makes all of this then interesting and powerful. So I've given you kind of the basic ideas behind it. Let me now talk a little bit about technologies, you know, and we are now at the time where we are trying to build these machines and give you a perspective. And there's many ideas, many quantum systems now out there where we learned how to control these things and where we have very good candidates to build these kind of quantum computers. And I just present here examples like, you know, this is the trapped ion and we'll talk about afterwards. We have, of course, superconducting qubits or superconducting devices. This is extremely promising, and there's a strong competition at the moment between ions on the atomic physics side and the development of this of the superconducting circuits with quantum dots, cavity QED, and V centers. So there's a whole zoo of, you know, quantum systems out there that we are learning at the moment how to control. And what I want to do now is a little bit focus in on one of these examples, which will be the trapped ions over here. And I want to mention here the Nobel Prize given to Dave Wineland and Serge Roche, who developed some of the underlying elements for single particles. We talk about many particles here, so this was for single particle physics of really ultimate quantum control of single particles. Of course, we would like to do it for n's, so this is sort of, we are building on the you know, on the developments of this Nobel Prize, which was given here some time ago. I emphasize that what we're doing is very difficult, sort of a man on the moon project, and I'll talk about my favorite thing over here, which is now the trapped ion in the following. And these are my colleagues over all of these years, and I want to mention particularly Ignacio Dirac, of course, in Munich, that we came up with these ideas, you know, and Rainer Blatt, Chris Monroe, Dave Wineland, who had enough courage to take our ideas seriously and actually build these devices in the lab. And it takes usually a long time, but to see at the end that this works is sort of very gratifying, I have to say. So what's the idea here? I showed you at the very beginning of my talk, you know, this string of atoms over here. These are ions, and they now store the qubit. Think of these single atoms that we hold now here in free space like little magnets, where the magnet can point up or point down. And these are our qubits in this case. And we would like to form then Schrödinger cats or superposition states of them, and we want them to compute and also implement gates over here. Well, if you shine lasers on these things, you can even make this string of ions somehow move. And the idea is this, that we came up with a proposal how to for example, implement the quantum gates that I talked about earlier before, using the phonons. These are these vibrations, but the quantum vibrations, not the very classical ones that you can see over here, as kind of a data bus, that communicates the qubits between between the various qubits here and allows us to perform these gate operations. I will not tell you the details behind it, but we have all of the elements ready, and laser manipulation, storage of these ions, and these ion traps and so on, which at the end allow you to implement the gates that I talked about earlier. Okay, so where are we sort of right now or here today? Well, these are sort of quantum circuits now in the lab, and I'm just not going to explain to you what they actually mean. These are quantum circuits that are sort of every day now in everyday life implemented in these machines. And you can see it's sort of getting to the point where we are really, perform rather complicated operations. So let me explain to you what these operations actually mean in terms of the physical device. Here's again my string of ions. These are my qubits over here that we would like to operate on. And we perform gates like by shining laser pulses on them. So you really have ions. If you take a laser, point it on one or the other one, and then perform rotations that correspond to these rotations on these Bloch spheres. Or you can shine these also from the side, or then also do readout by the method that we call quantum jumps. So we can make what we call in quantum physics projective measurements. We ask the particle, are you spin up or spin down, or 0 or 1? And we can make these measurements, and we can make them very, very accurately. So these operations can now be done with a fidelity, with an accuracy which is 99 point, and then there are several nines after that. The question is, of course, how to scale it up. And this is, early ideas from Dave Wineland, Dili Leibfried, where you think about taking these ions and shuttling them around. I stole this movie some time ago from Ike Chuang at MIT that sort of illustrates what one imagines to make a scalable processor out of that, where ions kind of are moving around, and then, they are performing operations. You check them out from some memory region, perform gates, and all of these kinds of things. And this is an example of doing error correction over here. So now the question, of course, will come along, what can we do with all of that? And I have to tell you that the original motivation for many of these things, at least that started me out in this track, was that I heard a talk by Arthur Eckert from Oxford. This was, maybe in 93 or 94. No, it was in 94, actually, where he came to a conference in Boulder, where I was one of the faculty. And he said, there's something new on the horizon. We should build a quantum computer. And I talked to you, atomic physics community, because you might be the one that could provide us with this thing. And Ignacio Ziraik and I were sitting in the audience, and we were listening, and then we were looking at each other and said, I think we know how to do that, actually, even. And the killer motivation that he sort of brought at that point was the famous Shor algorithm, which today we see as something that's far in the future in terms of realizing it experimentally on our machines. But I just want to give you the idea of what these early motivation ideas were. So why is a quantum computer more powerful? If I give you a number like 91, all of you probably can figure out that this is 7 times 13. But if I give you a number that's a little bit longer, you probably have some problems doing that. And if it gets even longer, so it's this is becoming a tough problem. And why is it an interesting problem? Because many of our crypto systems that we have are based on the inability of classical computers of performing very efficiently this kind of calculation. And I've just put a little bit of black and white over here together. Suppose that we had a quantum computer with 500-digit numbers. They have to be error corrected and so on. You need much more quantum memory than that. It will take us, age of the universe on the classical computer and sort of Mission Impossible, or a few seconds, depending on what kind of gate speed you put in, and based on the Shor algorithm, where you solve these things on the quantum machine using very, especially the possibilities that we have in the context provided by quantum mechanics. But let me emphasize, this was maybe very much original motivation for doing these kind of things. But it's also long in the future, because if you think about it, it will take a very long time to do that. We need fault-tolerant quantum computing, and we need actually 10,000s of qubits and millions of operations. We are definitely not there. This will take a long time. You have to do error correction, all of these things. So let's talk about something which is a little bit closer, and maybe also a little bit closer to the heart of physicists. And I want to talk now a little bit about quantum simulation of quantum materials. This is something which is a physics problem, okay? And sort of what we are trying to do here is this, that we are using now quantum computers or quantum simulators as special purpose quantum computers to solve problems that are of interest in the physics context. And we are sort of simulating here on controlled devices quantum physics, which is very hard to do on classical computers. Now by quantum devices and our quantum computers, and I think that this is one of the most promising short-term applications. Actually, this thing is going on right now in our labs, and therefore very interesting. So this is Feynman's vision, and let me explain a little bit. But before, let me say, what do you see in the background here? That's a picture that I got from Emanuel Bloch. I'm together in an ERC synergy grant with Emanuel and some other people. I'll show these afterwards. These are pictures of individual atoms that you can see over here. And this is part of these quantum simulators, and I will tell you a little bit about this thing. But this, again, pictures of individual atoms that we are sort of holding up there in free space and are doing interesting stuff for us. So what is a quantum simulator? A quantum simulator is not the aim to build a general purpose quantum computer which can do whatever you want it to be, but it's kind of a special purpose computer. There's no certain things to do really well and some other things not, okay? And that's the reason why it's sort of easier to build. So why is this interesting? Well, one of the promise of quantum simulation of this quantum matter is to design maybe new quantum materials, some of them potentially also with technological applications, maybe even in the context of quantum chemistry. There's some ideas around. We are definitely not there yet, or even then lattice gauge theories. So we wrote some recent papers about fundamental physics where we take lattice gauge theories that behind the standard model or quantum electrodynamics, and we are trying for the first time to put these things on quantum computers, where we hope that in the very long run we will actually benefit from the advantage that we have in building quantum devices and building large-scale quantum simulators. Just to give you sort of two snapshots of where we were, 2 years ago, we published a paper together with Rainer Blatt on one-dimensional quantum electrodynamics. So, to give you the feeling of what happened a few years ago, this is a universal computer in Innsbruck. It was a little bit ridiculous, 4 qubits, but you should be very impressed by the fact at the end, we were able to perform 220 quantum gate operations on these qubits. 220 quantum gates is actually a lot, If somebody had told me this thing 15 years ago, I would have said, you are nuts, okay? But now it exists in the lab, but it's a small number of qubits over here. And we were looking at processes like, Schwinger pair production in the vacuum. I will not try to explain to you the physics, but rather show you at this point something that we're doing right now at the moment. I gave a special seminar yesterday about a 20-qubit device, that we are programming over what we call the Innsbruck quantum cloud, where we as theorists have access to quantum machines in a sense of a quantum feedback loop, where we have a classical computer, that calls a quantum coprocessor that performs then, certain operations over here, feeds them back to the classical machine, and we can call, for example, in this context, these quantum machines 10 to the 5 times, and let part of the computations be done on the classical machine. Part of these things are done efficiently on the quantum machine. This is sort of an example of hybrid quantum classical algorithms that are hybrid, between classical computations and between quantum computations. And just to give you a feeling of where we are, this is calculating a ground state energy, and you should be impressed by the fact that over here that we have now 20 qubits here. We are doing optimization for 15 variational parameters, and we tell our classical computer, you're allowed to call the quantum processor 10 to the 5 times, okay? Because as you always say afterwards, the graduate students would like to go home and actually sleep a little bit to this quantum coprocessor, and I'm not going to explain the underlying physics, but this is sort of the state of the art that we have at the moment, and these are things that are run, via this quantum cloud. So we have this self-verification also, which is also one of the exciting results over here. It was sort of like asking the question, we of course would like to operate these quantum machines in a domain that's classically not accessible to our classical computers. But so if a quantum computer gives you back some result, how do you know it's right or wrong, okay? So you have to do some sort of self-verification of your quantum result. The quantum computer should not only tell you that's the answer, but also tell you, the confidence level in this answer. And we were able to demonstrate here in the particular context, that the computer gave you an energy for the ground state, but also the corresponding error bar. At the moment, with 20 qubits, you can all of these things still do classically very clearly, but there will be a time where the self-verification and how do we cross-verify quantum machines and all of these things is actually very important. So we have then here analog quantum simulation of material. I said, let me now switch over and sort of spend now the rest of my time talking a little bit more about other platforms that we have out there. In atomic physics, we have many other possibilities, not only the trapped ions, and I just want to give you a short kind of a, tour through some of these ideas and what people are doing, what are the systems that are coming in the future, and I still have to explain to you what these things are over here. And this goes back to these optical lattices, sort of like as an egg carton for atoms. So what's the motivation behind it? Yeah? So as I said before, we would like to do, say, quantum simulation of quantum materials. So what are actually quantum materials? Quantum materials, correspond to, well, if you build a material, you have your atomic cores, they form a solid and they form a lattice, of course. And the properties that you might be interested in, like electron transport and so on, all of that have to do with electrons that are hopping around, between these efferent atoms. We can sort of build a system with our cold atom that very much mimics, what's going on in the real solid-state system, but we do it on a completely different length scale. And we do it here by, for example, taking laser light to construct the potential landscape for atoms that can be in here, that can hop from side to side, kind of mimicking the electrons that would happen in a real solid. The main advantage is that, number one, the distance between this is not the usual angstrom that we have in a real solid, really tiny, tiny distances, but this is wavelengths of the light. Wavelengths of the light is a few hundred nanometers, and so everything is here much more expanded. What's the advantage? First of all, that we have control on this system, really down to the level of single particles. We can observe them. But on the other hand, of course, it also has the great advantage, one hand control, that we can also measure these things and really see what's going on with the individual particles. So it's like doing the same physics in a real material, but much expanded, but we are able to look at these things and have a lot of knobs that we can control the system and build systems that are of interest in solid-state physics. So I put this together here in one slide to sort of indicate, what the difference is between the ultra-cold quantum matter that we build in our labs with our optical lattices, and on the other hand, the real materials that, of course, we would like eventually then built in the lab that have maybe some very special properties. If I start out over here, real materials, they have densities 10 to the 24, 25 per cubic centimeters. Temperatures, if you go to the dilution fridges that I've seen downstairs in the labs in the basement, that are maybe millikelvin or something like that. And then, well, this is the world of quantum materials that have maybe very, very special properties. What we do is this, that we are sort of building a system like that, but on a completely different scale. For us, the distance between this is not the angstrom that we have over here, but it is, the actual distance is here, maybe a few hundred nanometers. And we talk about densities, see 10 to the 14, 10 to the 24, that are orders of magnitude more dilute. So actually the atoms in this lattice, this is, as you can see over here, it's 100 times thousands thinner than the air that we have around us. And the temperatures are not here millikelvin, but they are a few nanokelvin. So we are trying to build systems that are completely analogous, and you might ask, what does the property of this thing have to do with this? There's a very simple argument behind it, and this is what we call in quantum physics universality. When I have a quantum particle, and this quantum particle is moving, it has a certain wavelength. It has a certain de Broglie wavelength, and this is given, let me call it lambda over here by the scale. And then we have a distance between this particle d, and there's one dimensionless parameter, lambda divided by d, and we are in the quantum regime. If the temperature is so low that the wavelength is actually so large that these wave packets all start to overlap. And if this parameter is the same on the left and the right-hand side, then it really means that we are able to build here systems on a much expanded, much lower temperature scale, but that's exactly what we're able to do in atomic physics. And of course, the great thing is, as I said, we can look at these systems. This is the famous quantum gas microscope where we can watch these individual atoms in there. We can perform measurements on them. And if you want to see how a real experiment looks, this is from Emmanuel Bloch's lab. This is from our ERC synergy grant. This is how these experiments are. So they are not pocket-sized version, at least not yet at the moment. So let me sort of move on and give you as the last ideas in this context now here, a little bit what the future is. Because I think that we have sort of, in atomic physics, we are approaching the point where we are trying to learn how to assemble complex quantum systems kind of bottom up, okay? So we would like to take single atoms and then sort of then put them together and construct something more and more complex quantum systems. And just to give you a first glimpse at these possibilities that are now arising, I want to tell you now a little bit about this building up of quantum systems one by one. And I will illustrate these things with a tweezer, but we're not going to make a tweezer that you see over here. That, of course, is so well known in the context of biology. And I was very happy that Arthur Ashkin, now 96 years old, got actually the Nobel Prize, last year for the invention of this tweezer. Steve Chu, of course, collaborated with him on many of these things. And tweezers is very important and famous in the context of biology. So it allows us, to manipulate whatever you have in this context. We want to manipulate single atoms and build with tweezers sort of complex quantum system. So let me tell you in this sense what the idea is behind it. And if you have a focused laser beam, this should be a focused laser beam, this red thing that you have over here. We just take really a light beam and you shine it in, you focus it very much. Instead of the cells that I showed you before that we have in biology, we would like to take now a single atom and then actually put it inside. So this is a single atom that is here stored in the tweezer. And imagine that you not only build one tweezer, but what you do is that you build many of them, okay? And you would like to load them atoms into these tweezers. Actually, sometimes you're not lucky in loading an atom. For example, if you loaded 2 of them, and then you shine laser by looking, oh, is there an atom, yes or no? Then the 2 atoms destroy each other. If there's one atom, of course, it will fluoresce, and you can see it under your microscope. So in this sense, we can very easily check, is in this tweezer an atom, yes or no? Here not, yes, yes, and no, and so on. And the great thing is that we can now see that we have single atoms that we stored in our tweezers. But what we can do is this, that since I observed or have this information, I can, of course, just delete the one that have no atom inside and move the other ones here together. So you can see that what we have done here is that we have assembled here an array of tweezers with exactly one atom inside. Think of this atom like being a qubit or the particle of interest, which is like the building block of your complex quantum system or the computer that you would like to do. Here's an example from an experiment from Misha Lukin's group. He gave me this slide here. You can see that this was loaded, here's empty ones, and so on. And what you do now in a classical computer that looks at this fluorescence over here, just collects all of these things and shifts them together. And this is now a register. Before talked about 20 qubits with ions. Okay, this is now in this case 51, I guess it was. 51 Rydberg atoms that are stored in these tweezers that we have over here. And if you're good friends with experimentalists and you pay them a beer at night, of course, they can also do fancy things like make any arrangements over here that you asked him to do so. Well, it costs 1 beer. Maybe in the meantime, the price has gone up, so you can maybe order a T-shirt with that. But this is really single atoms, we call this atomica font, how to sort of put any patterns. But I guess the basic message is clear. We can write sort of bottom-up, construct rather complex systems where we have particles in free space and we can put them wherever you would like to do. And let me show you here the example from Antoine Brouvet's in Palaiseau from a paper that came out in Nature last year. Of course, if you live in Paris, then you have to do an Eiffel Tower. It's very clear. Yeah? These are all structures that you can build in 3D and 2D and so on, in free space where you can assemble any atoms that you would like to have in the structures that you would like to have. Notice, however, you might ask yourself, what's the distance between these atoms? This is not, the distance between these atoms is actually pretty large. It's maybe something like 3 or maybe 10 micrometers or something like that. So actually, there's a big distance between these atoms over here. So you can see that we have a very beautiful way of assembling our artificial, quantum matter from single atoms, kind of bottom up. But you will ask, well, you were talking about gates before. You must have these things interact. How do you make them interact over a distance of 10 micrometer? And this is the problem, of course. If I just have one atom over here, this is the first tweezer, this is the second one, and I have a distance of 10 micrometer. If you calculate the interaction strengths in your ground state of your atom, it's microhertz. So this is a way of saying 0. Okay, it's 0. So the challenge is, of course, then to come up with ideas. How do we make these atoms interact? And the answer, or one of the answers of doing this, is actually Rydberg states. And let me sort of almost now conclude my talk by giving you a mini tutorial again of 2 minutes of what Rydberg states are and how we can actually increase these interactions here by many orders of magnitude and to make them useful, and at the end having to do quantum gates. Maybe some of you remember from your high school physics, you know, the Bohr model of the atom. You have an electron orbiting over here. This is sort of semi-classical quantum physics here. This is single valence electrons here. In this case, this is just sodium as an example. But of course, there's also, you know, possibilities of exciting them energy-wise to very, very high-lying state. And what do I mean by that? You put in a laser on these Rydberg atoms and you try to excite this electron to something that becomes a really huge orbit. You know, really, so these are now big atoms. These are not these really small ones that we normally have. These are now atoms where the outer electron is really sort of highly excited, and it's really a huge object. This is a microscopic object. We made out of a single atom a microscopic object, and Rydberg was the one, of course, that described all of these Bohr orbits, Rydberg excited states, you know, by, you know, this is the original formula down here, describing it by this famous Rydberg formula. So suppose that you take something like n equal to 50, you know, then what's the scaling? Well, actually the scaling is that the radius over here goes with the principal quantum number of your Rydberg atom squared. And if you start to put the number, this is 2005 times larger than the ground state atoms. So these are becoming really, really fat and big atoms. And it will, of course, then also understand that they then interact much more strongly. And that's exactly what we, of course, want. So if I take a baseball over here in the baseball stadium, that's sort of the ratio, you know, of this thing relative to that we are sort of inflating our atoms over here. And all of this has very interesting properties, like the lifetime actually increases, you know, if you go to higher states, so they are long-lived. And if you now have two atoms that sort of dock to each other, one over here and the other one over here, look at the scaling, you know, with a power 10 to the power 11. I've never seen this in physics, a power log like this. You get a very strong interaction over a distance between these atoms. So we have now a handle in atomic physics to make these atoms that we are sort of self-assembling, and these lattices dock to each other, perform gates, or do what kind of interactions that you would like to design or use in your context here. And you can see instead of this really ridiculous number here, we're now up to scales like 100 megahertz. This is 12 orders of magnitude. So we have mechanisms in order to do our engineering of this artificial quantum matter, you know, that allow us to get very strong interactions. And of course, at that point, you can think about gates, and the underlying mechanisms of this thing is something that we described in papers with Misha Lukin and also Ignacio Cirac about 15 years ago, but they now exist in the laboratory. So let me go sort of converge now to the end of my talk here by simply saying that I've really talked about quantum computing here. We have different, you know, versions. Superconducting I've really talked about. We should also talk about big-scale quantum networks. We would like to network quantum computers here. I've not mentioned protocols for quantum communication where we build a quantum internet. And that's interesting from the point both of quantum communication as being secure. You know, maybe you remember these satellite experiments that were done in China. There was this very famous telephone call between Anton Seiling and Vienna that docked via quantum cryptography to Jianwei Pan in Shanghai. All of that. So we have time has come, you know, where we have these kind of applications. But all of this promise that we have right now, you know, in terms of quantum science, becoming more and more also, you know, a quantum technology, has of course also triggered. Just show here the example of Europe of this. There was this famous quantum manifesto. That we have now these famous flagship programs, you know, that provide a lot of money for quantum. Whenever you're doing quantum, you're good, okay? And there may be money then available, okay? Many people are attracted, I guess, by that. You know, and in Europe, we have all of these possibilities here. I really want to point out that in the context of atomic physics, from my angle, there's a lot of opportunities for us because we are the ones that build the best atomic clocks. We are the ones that know how to build computers. We can combine them. There's you know, a lot of possibilities out there. And of course, this has triggered, you know, all of this funding, like is China winning the race? If you go to the US, I mean, the word China appears as every second sentence in this whole context. Of course, there's an American program now also in this context here. Just as a side remark, of course, all of these companies even now started the race. This is this indication that Google would like to demonstrate quantum supremacy, outperforming classical devices with a 72-qubit device. I think it doesn't work yet, okay, in the way that it was advertised. This is now a year ago. Will be interesting to see what's coming out here. But there's many startup companies, like my colleague Chris Monroe in Maryland is taking these ion traps very serious and has formed a startup company. Honeywell has an ion trap division now that has about 100 people, and they indicated this on the website a few months ago. And you can see now, if I sort of try to summarize my talk now here, I started out with some basic science. You know, we started out with Planck and Schrödinger and Einstein and all of that, and was really basic science at the beginning of last century. And strange stuff like Schrödinger cat that normal people don't really think are, you know, exist, to applications, you know, but also then, you know, to spin-offs like building then the best atomic clocks. And I think that this is a very beautiful example of basic science moving more and more to technology, but then also changing our everyday life. Because, you know, why is atomic clocks useful? Well, atomic clocks is useful because we have, for example, at the end, the possibility to build better GPS systems. And what I, as a physicist, I'm very excited about is this, that we're building quantum computers that at the end maybe are coming back to all of us as new tools in physics, you know, that allow us with new tools, new instruments to be able to make some new discoveries that sort of future generations of our physical understanding will be built on. This is the experiments that I showed you experimental results. These are some of the students that are working with me at the moment and postdocs, and Rainer Blatt has this infinity of, I think, 40 people in this group that do all of these various experiments. That's very complicated technically. And I'm very happy in Innsbruck, you know, with these kind of collaborations that we have in this context. And this is the Quantum Institute that we have in Innsbruck. There's a whole international community, and I put just randomly some photographs and, you know, some of these devices that we have over here. A lot of collaboration, of course, with Misha Lukin. I mentioned Ignacio, of course, anyway, and Rainer mentioned before Dave Wineland. And Didi, they are, of course, also now doing Eintrap quantum computing, and Eugene Polsik at the Niels Bohr Institute. And Chris Monroe is another Eintrap, and Jeff Kimball, who is a atomic cavity QED person, you know, in the context of, for example, quantum communication, of all of that. And this brings me to the conclusion, and you can sort of read it yourself. And after this talk, you might even get this Dilbert joke over here. So, how's your quantum computer prototype coming along? Great, you know. The project exists in a simultaneous state of being both totally successful and not even started yet. Can it be observed? Well, this is this question of, you know, destroying quantum superpositions if you start looking. Can it be observed? That's a tricky question. Okay, so let's observe what will happen in the future in this whole context. But I think that we have some very exciting times ahead. And I know that some of you are quantum physicists, and you will contribute, of course, to this coming quantum revolution, both in terms of science and also technologies. Thank you very much. And this is Innsbruck, you know, where I come from. So over this year, we have much more snow. This is where our institute is down there. This is New Year's Eve from the mountains. And this is my thank you. And this was my group just this winter. You can see there was a lot of snow. We had 6 meters on the mountain. So what you can see over here, we had now sort of 6 meters of snow now over here. It's not as a... So if you want to come for skiing or good physics, pay us a visit. Thank you very much.